Okay. Now let us go back to resource allocation and apply the VCG to resource allocation. So we'll now show what VCG, which is a general mechanism, remind you, what it would do for resource allocation, and then we want to make something which is inspired by that, but a bit different. So the classic VCG, which is general and is applicable to any mechanism where you choose one of the options, and so on and so forth, and you may charge prices. If we apply the classic VCG to resource allocation, then what would we get? Then the strategies of player I would be simply all the values, all the value functions. The strategies are all the value functions. You need to supply to the VCG exactly your whole value function, whatever it means. So if it's finite, you need to supply some table. What is the value for each of the options? If it's infinite, you need to think how to supply that. Anyway, that's what the mechanism requires. Now the allocation optimizes the social welfare according to what you have supplied. What it means formally is that if you denote by T the space of all the allocations of T, of total size resource T, then the allocation based on this V, the tilde is the declared thing, unlike the actual, which is just V tilde. The declared is denoted by V tilde. So the allocation based on this V tilde is basically an allocation maximizing the total value according to what, again, to this tilde, according to what you have supplied to me. I'm just translating what VCG tells about our case. The payments are, you should be able to do it yourself. I mean, the payments are this H function based on something which only the others, or only based on what the others supply. Which something, whatever, can be whatever, minus the sum of what the others obtain according to the declarations in this allocation we have decided upon. I mean the mechanism we have decided. And so the utilities are what the utility of player I is what the player I actually, regardless what she declares, what she actually feels, that's not tilde, minus what she pays, which in the case that she reports truthfully, which we know for VCG is weakly dominant, that in the case she reports truthfully, that's just what she experiences minus this TR if everyone reported truthfully. So then the sum of the V tildes is just the sum of the V's, and together with the V of R, it's simply the total sum of the V's, minus HR of V minus R. Again, assuming that V and V tilde are the same, because we assume that they reported true. So basically, in this case, the utility of the player is simply the social welfare minus this HR. In general, the price of the user in this case, user I remind you that what we defined as the price is basically what the user pays divided by what the user gets. Because what the user pays divided by what the user gets was what the user is willing to pay divided by the price was what the user gets. Obtains, and therefore price is what the user willing to pay divided by what she obtains. Now this payment divided by the allocated amount in the mechanism may differ in general per user. I mean, for the same user, this can be no, not for the same user. Eventually, different users may, in this sense, obtain different prices. So this ratio may differ from user to user. Usually it will be something, but it may differ from user to user. So in the application of VCG to our case. The problem is that first of all we need to somehow supply this huge information about all the value functions instead of some scalar value. How much exactly you want to spend, not waste, to spend what we did before. So we need to supply much more. And what the mechanism returns, if you look at this in terms of the prices can be not the same from user to user. So indeed, we've proven that this profile is weakly dominant to tell the truth, and then it's optimal and all that. But the requirements of what you need to keep in the mechanism and what the mechanism eventually gives to you, which is an optimum allocation, and the charges of prices which can be seen as different prices per user, that's too much. Now, especially the problem is, of course, given the mechanism, these value functions, all the value functions, so even if you have just a finite domain, the value function, how much information you need to do. So you have a domain of X options and the range, say, so each element of the domain can get something from the range. Y options, so how many functions like this are there? So each of the elements of the domain can get Y options, and that depends on what the others get. Well, it's of course dependent because let's say continuous knowledge, but if it's a finite domain, so the continuity does not tell us much. So what I mean is that it seems like it's order of Y to the power of X options. So it's definitely something huge. We need to limit this communication of the whole value function to some one parameter thing. That's important. That's not practical to communicate all the value function. Now, what we do allow, because we want to have something better than what we did have, I reminded that price anticipating agents, it was guaranteed to have at least 3/4, but not necessarily this is good. So what we do allow to improve that is that we allow to have this allocation, which basically can be seen as different prices. That's okay. Okay. Which user charges price, which a price which can be eventually each user, charges an amount which can be translated in the terms of what the user is charged divided by what the user gets to different prices. But that's kind of that's fine. Not too much information, unlike the strategy. So what we just need to do is we just want to limit the VCG to the one parameter space of what you communicate to the mechanism. But then we also assume that the VCG, of course, will then not hold. So instead of requiring that there will be dominant or weakly dominant strategy profiles, we just demand that that this optimum thing will be in truthful and optimum thing will be in inertial equilibrium. So we demand something weaker. Because of course, if it's in a weakly dominant profile, it's inertial equilibrium, but not the other way around. So we constrain what the input can be to the VCG, and then we also understand that the output will be not as good, and that's what we call it Scalar Strategy VCG. So the strategy should be scalar. Or if you look at this from the point of view of what we did before, we actually extend what we did before to prices which may vary from user to user, and then we also extend what we expect because we want to get a better efficiency, which we will. So it depends how we look at it, as an extension of what we did before, or as a so that we allow the prices to differ, and then we get a better efficiency, or as a narrowing of what VCG does. When we actually require the communication to be one parameter communication, we'll see what it means and how we can communicate a huge function as a one parameter thing. And then we also understand that we'll get something weaker than VCG gives. Okay, so we just recall, let's now define the things. By the way, this idea that you get, okay, that you tell, there is a mechanism that I want, but I actually want, I don't want to fulfill, or I'm not able to fulfill all the requirements, so I'm going to fulfill only some of them, but I would like to get something that it used to give me, but maybe a bit less. This kind of trade-off is very common in computer science, and that's just one of a multitude of such examples. That you basically have something, and then you're inspired by something, then you say, no, I want to have this, but a bit different. That's common. Okay, now let's get to the formality. So we recall that we assume that a set of value functions, the original value functions, you will communicate one parameter, but the original value functions, any set where each v is concave, strictly increasing, and continuous over the domain of 0 to infinity, quite natural. Besides the concavity, the requirements are quite reasonable. They also require that it's going to be continuously differentiable, so it's differentiable and the derivative is continuous. And the derivative from the right in 0 is smaller than infinity. That means that the marginal addition, what you get from getting something from 0 at point 0 when you don't get anything is smaller than infinity. We are going to actually at some point see what happens if we don't assume this. So that's not something we always need. This last assumption. In addition, we are going to now define a new class that's going to be the parameterized by one parameter class. So we're going to define this v hat, like we had tilde for what we declare here, it's hat. So each user chooses a function from this v hat, which is a space of functions parameterized by one parameter. That is the parameter, which basically is a function of the first parameter, which now is denoted by a dot. It will be the amount of resource allocated. And theta is not a part of the function, rather a parameter which tells us which function we choose. It's a very abstract thing. It can be some function. Theta tells us which function we choose. So this is a real number, so that's scalar. And we assume that this v is subset of v hat is subset of v. So it and in addition, each f in this v hat is also needed to be strictly concave. So like something like, I don't know what the you have d sum d squared, and theta can be times theta. So then you have a strictly concave function. Another thing is that we have the option achieve. We have the option to achieve anything by derive. The derivative achieves any value. What it means that for any value you would like to achieve from 0 to infinity, and for any d which you substitute to the function as the argument, there is a parameter theta such that if you look at this derivative is always by d because it's a function of d. It's not known if when you look at this as a function of theta, it may be not. It's not even a differential. So I here just emphasize that it's the derivative by d by dd, but it's basically we can always denote it by it's not a partial derivative because there's only one parameter in this sense, and we denote it by prime because it's only that we derive by d. Theta is just a parameter. We can of course look at this as a function of two variables, but unless you say otherwise, we look at it as a function of one variable. So theta is the parameter. What we basically say is that for any variable d inside the function, and for any value we would like to get gamma, we can find the theta. So we can find the function such that if we substitute to its derivative d, which we are given, we obtain gamma, which we are given. So for any input and output, there is a function that brings this input to its output, but not that function itself, but rather its derivative. Okay, hope you understood that. That's important. So again, these are the functions we are going to give to the to the VCG, the inspired by VCG is not VCG, it's called Scalar Strategy VCG. These functions are inside V, also strictly concave, and also this requirement of the derivative obtaining anything we want. We need in the future just to be able to tell, okay, I want a function which derivative at this point is exactly that. That's something we need, and that's the theta is what we're going to communicate to the mechanism. We'll see, of course, what does it mean to be truthful here, because apparently, if V is a much larger space than V hat, how can I be truthful? I may not have my function, my value function in V hat. But then we're going to see what it means. It's going to have the same derivative and so on and so forth. So, that's what we have. And the output of the mechanism, given theta, the mechanism outputs a allocation, d of theta, which maximizes the total utility according to what you give them, to what this V hat. Now, the strict concavity of each V, of course, hat, not R hat, but V hat. Excuse me. The strict concavity of each R's V, of which R, which player R, V hat is strictly concave. I think that. So the so the strict concavity implies required a value in addition to B and V. Since in V hat I also strict concavity. So the strict concavity in V, this function, implies the solution is unique. Not only does it exist, because it's continuous and the domain is with respect to the possible locations is compact, it's also unique, and the payment for agent I is defined as, again, in this VCG. Here we are free to define it as in VCG, and that's what we do. Some function h of what the other players bid minus the sum of what the other players derive according to their bits. Bits here are these functions we have. Now, functions basically, what is the same function, simply parameterized by this step. So the actual functions are functions sum v of r, but here we just will tell see how the class will want to choose that we had some function parameterized by one parameter, it's a set parameterized by this theta. Now, not necessarily, but this h can be defined in the following way, inspired by the Clark pivot rule, which we saw for the general VCG. It doesn't have to be, but it can be. So, what will that then be? Then it will be the sum of what the other players get according to what they tell to the heads, if we optimize for that sum. So what could they get if we just wanted the other players besides R to optimize what they have? And then, as before, as in the case of the general VCG, Clark pivot rule will get that the payment will be what the others get when we optimize for what they can get alone, minus what they actually get when we optimize for everyone. So exactly, you pay, our player pays for what she kind of takes from the other player. Okay, so basically, the mechanism gets less than the VCG, that's our requirement, but it outputs something the same basically as VCG would, based on what it has got, based on those heads. Now, so the output is G, which optimizes the strict concavity implies it's unique. Okay, not for each R, but for each. Okay, let me just for each strict concavity, each head. Price is unique. Now the payment is defined as this H minus what others get, and we spoke about how you can also basically use the Clark pivot rule, and then the total utility of an agent is basically what the agent derives, regardless what the agent actually derives. So the value of the agent, not necessarily the head, and plus what the agent pays, or basically, minus what the agent pays, which means that plus what the other agents say they derive, minus this H. And theta vector is a Nash equilibrium if basically for any agent there is no rate of deviation which strictly improves what the agent does. So for any agent R, for any theta prime of the agent, what she would get if she moved from R from theta R to theta R prime, when the rest did what they did, would be at most as good as what she got before. Okay, so now we look at this Nash equilibrium in this new mechanism. So we have defined basically a game by defining this mechanism, and we've defined what it means to be a Nash equilibrium there, but it's basically not a new definition, that's simply a translation of the general definition of Nash equilibrium for this case. And now the question is, what can we tell about the Nash equilibrium of this mechanism? We hope that this mechanism has some nice Nash equilibrium, like the original VCG has some nice, first of all, it has a monotone strategy, a weakly dominant strategy profile, which here we'll see does not have to be the case. But here we will show that this new mechanism allows for a Nash equilibrium, which is good in the sense that we'll see. So it's truthful and efficient and so on. So analogously to what we showed about the truthfulness of VCG, here we also connect real utilities and Nash equilibrium, the same as we connect real utilities and dominant strategy profiles in VCG. Here we connect this with weaker, because it's only Nash equilibrium, not necessarily a dominant strategy profile. But again, given that we weaken the requirements, it's fine. What we basically prove is not yet about truthfulness. We prove that the vector theta is a Nash equilibrium if and only for any player the allocation. Pay attention, here it's about theta, here it's about allocation. But what we basically show is that so yeah, there was a typo. Now I fixed that. Let's get back, and so the correct version is as follows. So the theta is a vector, theta is an equilibrium if and only if for every player the following holds. The allocation which results from the theta is maximizing the following expression: the actual value that the player has plus the sum of the values of the others according to what they tell, according to this step. So that's actually quite a simple thing to connect your value and what the others tell. Truthfulness to equilibrium. It's not really maybe clear what it is. It's actually very simple lemma. It's not trivial, but it's simple because basically what we see that in equilibrium everyone has to maximize that thing. So assuming that H is not dependent on what player I tells, what is dependent is basically the actual value of player I plus the reported values of the others. That's kind of the same, but again, it's not exactly the same because here you look at this D, which is chosen according to theta, and here you look at the D, which maximizes the sum. So there are certain small differences. That's why we have a lemma, but it's not so complicated. So the proof is in two directions. So because it's an all-if, so first we assume that the condition above holds. So that for each player, D is maximizing that expression. And what it means is that for each player, theta R is in particular maximizing this expression because it can never be better this can never be better than the optimum value of the expression when D is anything in C, so D is any allocation. That's the best thing you can have. So if D of theta, and again I need to fix it, D of theta is optimizing this expression, let me fix that. So if theta is optimizing the expression, what it basically means is that theta is the best possible, because optimizing the expression is the best you can hope, because here the D goes over all the possible D's. So also theta then is maximizing this expression. If that happens, then this happens. And that is exactly by the definition the best you can do in order to maximize your utility, recalling that HR does not depend on what you do. So that's an Nash-equilibrium. So assuming that the condition above holds, we prove that theta is a Nash-equilibrium. Now we need to go to that direction, and here we assume there is a problem with the type setting. But okay, let's just explain and then I'll fix the problem with the type setting. So in that direction, we assume that theta violates that requirement, and then we prove it's not an equilibrium. So it is an equilibrium if it violates for some R, at least for some R it violates, it means that it's not an equilibrium. So now I need to fix the problem with the type setting. So if theta violates that requirement, yeah. So first, here the compact set of the possible allocations is closed and bounded. In R, it's a compact set. I mean, in a finite dimension equivalent space, it's a compact set. So the continuity of these functions, which maximize, implies that there exists a D star, which actually attains the maximum, so which is an argmax of the expression. Now we have these first order optimality conditions, and they hold conditions with first order derivative, they hold for this distance. Now let player choose some theta R prime, that of course will be the deviation we'll see, which is profitable. But that's let's choose some positive theta, such that the derivative, if we look at this function, the derivative of that function in d star r, will be exactly the derivative of the given v, it has to be v, not u, apologies, in this star. So I remind you that we demanded, okay, I need to fix that, it's not u, it's it's v. I remind you that we chose, we required that the derivative at any point can achieve anything if you choose the right theta. We choose the theta such that the derivative of this v hat in dr star r theta will be exactly what the actual function, the actual utility function is. So we of course are not always able to tell to exactly pick our utility function. Maybe it is not in this v hat space, but we are able to pick something in v hat space that will have a derivative such that at this point it is equal to this. That's kind of the analog to truthfulness. Yeah. So this is possible by our assumption, as I said, about this family. Since the optimality conditions only involve first derivatives, this d hat satisfies also the optimality condition. So we know that it satisfies the optimality condition. This star, satisfies the optimality conditions for this. And since the derivatives are the same, it also satisfies the optimality condition for the sum of what everyone just declared, not necessarily what they actually have. So let's just recap and continue. Assume, as usual, I kind of repeat in the beginning of the slide the main conclusions we've made till now. Assume that theta varies this star. Okay, let me change. This star, no, not this star, the d which is chosen by theta is optimizing that expression, and we need to prove it's not Nash-free. For some r, it varies. Now, we saw that because of the compactness and the continuity, there is a d star which actually optimizes. There is an allocation which optimizes the expression. Therefore, the first order optimality conditions, all those derivatives, hold for this case. Now, that this star also satisfies the optimality conditions for this maximum, because that's also how we chose this theta star r, theta prime r. Now, since the maximum is unique because of the strict concavity requirement, remember why we had this weird requirement? It means that actually this have the d, when you have this d, the d which is chosen when pi r deviates to theta prime r is exactly the same as the star. So the others do what they used to do. Player r deviates to theta prime r. The d which is chosen is exactly the star. Now, finally, if you assume that theta violates this, and again, that d of theta, the d which is chosen by this theta, is maximizing this expression, then the utility is going to be strictly smaller than what happens when we look at this optimum d star, which optimizes the expression. We also subtract this hr, and here we write the utility. We remind that it does not depend on what the player r chooses, but we need to subtract it in order to look at this utility of the player. So that's the assumption that player R does not manage to optimize that expression by theta. Now, then you have the equality, which stems from the fact that this d, which is chosen when you deviate, player R deviates to theta prime R, and the rest do what they used to do, is exactly the same as this star. And that's equal to this utility of player R. And she deviates, she's the only deviator, the rest do what they used to do. And thereby we have proven that theta deviating from theta R to theta R prime actually has strictly increased the utility of player. So it's a strictly profitable deviation, therefore this original vector theta was not Nash equilibrium. So that's the end of the proof. So if that condition does not hold, it's not Nash equilibrium. Before we prove that if it does hold for every player, it is a Nash equilibrium. So indeed, we've proven that lemma, that is a Nash equilibrium, theta is a Nash equilibrium if and only if for every player what is chosen based on theta optimizes the expression. Now we may forward to prove now actually the central part statement of this part. In fact, it is called corollary, not theorem. But the thing is that it's simply going to be quite a simple corollary. We're going to prove that there exists an efficient Nash equilibrium where the users are locally truthful. What does it mean? That the derivatives at the point where they choose their theta are equal to the derivative of the original function. So what they report, if you look at the function they report based on player R reports on theta R, the function is simply this v hat of theta R. The derivative of that function at the vector which is chosen based on all the reports is equal to the derivative of the original function Vr, the actual private value of this player at this vector which is chosen based on the report. So the derivatives, in that sense, it's truthful. The derivatives are the same. So it's truthful and efficient, but it's only guaranteed that there is such an equilibrium. We don't know whether it does not have to be a profile of monotone strategies, of dominant or weakly dominant strategies. Moreover, we will see that there actually does not have to be a profile of weakly dominant strategy. That's something which we need to remember. In that sense, the conclusion here is, as expected, weaker than the conclusion in a VCG. Well, we have definitely constricted the reporting here to the mechanism, so it's expected that we'll get something weaker than the VCG. And so formally, the corollary is as follows. Given this scalar strategy VCG, the following profile is an efficient equilibrium. What's the profile? So given a system of a solution of system, of an optimal solution of system, which exists because of a continuity and of this objective function of the system and the compactness of the domain of all the allocations. Let each player choose theta R such that the derivative, when you choose theta R, the corresponding function, if you look at its derivative at this point, corresponding to this ds, called the system optimally, will be exactly equal to the derivative of the actual function in this ds, and we assume it's possible. Remember, we have this assumption that at any point you can have any value of the derivative if you choose the right theta. And that choice will then fulfill that basically the chosen d by the mechanism, the chosen d will be equal to d of s, which solves system optimum. Maybe with confusion. So basically we're going to get something which is optimal, which is truthful in the sense that the derivatives are equal at this point, and it's a Nash equilibrium. It's a truthful, in this sense, optimal Nash equilibrium. Like the conclusion of the VCG, simply the truthfulness here is naturally constrained, and it's only for a Nash equilibrium, and we don't claim anything about dominant strategy profiles because there may be no such profile. And the proof is simple. So the proof of the scholar is simple. The choices, as we said, the choice of theta is possible. The choice of theta is possible. Choice of the different players are possible because of the compactness of the domain of allocations and the continuity of the actual utility functions. The system is solvable. So there is some D S which solves system optimally. And then we assume that there is a theta such that the corresponding function's derivative at this point, ds of r, will be exactly equal to any value, in particular the derivative of the actual value of player dr at ds of r. So this is also achievable. Now, since the optimum of d theta is actually maximizing the sum of the reported, since the optimum, yes, maximum. Second. We choose something which maximizes the sum of the reported values, and that's unique because each reported value is strictly concave, according to our assumption. And the optimality conditions involve all the first derivatives which are chosen to be equal. Then the value which our mechanism chooses has to be the same as the value based on which it was built because of this equal derivative. Analogically, this D of S satisfies the lemma. I remind that it means why they satisfy the lemma. Again, because it also optimizes something and optimizes something. No, sorry. Okay, yeah. So because of the uniqueness, yeah, right. So because of the commanding conditions, again, involve only the first derivatives and the equality, it also is the lemma. So it also, so theta is also Nash equilibrium. And therefore, we have basically shown the result on allocation is equal to ds, and it's a Nash equilibrium, and ds is efficient, so it's everything. Now, despite this nice result, there can be other Nash equilibria, possibly inefficient. So it's true that there is this equilibrium of this, which we've shown how to construct, and that's efficient. But there may be inefficient equilibrium. Actually, it's similar to the classical VCG. That it shows that there is a weakly dominant profile, which is optimal. But there may be other weakly dominant profiles, which are actually suboptimal. Because weakly dominance is not unique, unlike strict dominance. So the same here. Not the same, but analogically here. Can be other Nash equilibria, possibly inefficient. Actually, in this case, we are going to see that not only that there are several Nash equilibria, but also there is no weakly dominant strategy profile. But let's look at this example. So consider R identical player with exactly the same strictly concave utility. Assume player 1 chooses theta R, satisfying that the derivative of this v hat, when you theta 1 dy defines some utility function from this one parameter family, and the derivative of this function when the player gets everything of the resource is greater than the actual derivative of this utility at 0, while the other players 2, 3, and so on till the player R, they choose theta R such that the derivative of, again, the chosen value function at 0 is strictly smaller than the actual derivative of the actual utility function at the maximum value of the resource. Now, these conditions together with the concavity implied condition that the derivative at the end is, I mean, when you get mostly all the resource is at most the derivative in the beginning. So the derivative cannot increase, and then that's from the concavity, and then it can be shown again. It's a calculation with all these calculus related things we don't do here too much. So the conditions of the lemma are satisfied for all R. So this is by that lemma group is a Nash equilibrium. When player 1 gets everything, so they're satisfied for theta when player 1 gets everything, and the other players don't get anything. That's a Nash equilibrium because it's a choice. When we choose theta 1 satisfy that, and choose theta R for every other player satisfying that, then the D, which is chosen by this theta vector, will take everything to player 1 so much she will enjoy that it will optimize what we have. Again, we can prove it, but basically that player R enjoys at the end even is strictly greater than what the actual utility, the same for all the players, is in 0, which is greater than what the actual utility is in C, which is greater than what the others enjoy at 0. So basically, it can be shown that the optimum condition will give everything to player R, and this is a Nash equilibrium by the lemma. So we have this Nash equilibrium, but not optimal. The only optimal solution for the system of allocation is equally allocate everything to everyone. It's not optimal. But we have this optimal solution. Moreover, in this game there is no monotone, no weakly dominant approach. Because when the others get nothing, when the others, take this theta, it's the best for player R to take this theta 1. But when the others do something else, it's best to do something else, which eventually results in this optimal location. So there are two equilibria, and also there is no weakly dominant strategy. Just if you were wondering, it's indeed true that there are cases when there is no weakly dominant strategy at all. So it's not like we just didn't manage to prove that there is such a profile. No, there are cases when there is no weakly dominant profile. Okay, so there are equilibria which are not as good as we've shown, but we can actually require something which will force the equilibria be as we want, and that is the following. So in the example above, player 1 bid too high, basically. She bluffed. It's the same utility, but she bid too high. And the rest didn't want to compete. That's the intuition. She chose theta 1, which was too high. Now, what we can avoid such a problem, but we can guarantee participation, thereby cause competition, by assuming everyone has an infinite marginal utility at 0. But that's exactly what we didn't. So we don't want to assume this thing we said in the beginning. We dropped this assumption that actually the marginal utility in 0 is finite. We assume we didn't use it, and we are going to drop it here. Then we will be able to prove that every equilibrium, we won't do it here, but we'll be able to prove every equilibrium is optimum. So our proposition is as follows. Assume that the marginal utility, so the derivative which you get in 0 from getting more is infinite for every player, so everyone infinitely wants to get something when having nothing. Then any equilibrium will satisfy that the resultant allocation is optimal for the system. That's something we are going to. That's something which cannot happen in this example. In particular, if v derivative at 0 is infinite, we cannot choose something which is strictly greater than that. Okay, the proof uses the lemma and the optimality conditions for the based on the first derivative, the optimality conditions for the system of allocation. So we have basically, to wrap up, we relax the requirements of the input to the VCG. We want it to be one-dimensional, and thereby, of course, we obtain something weaker only in an equilibrium, but we obtain still that there is some kind of truthfulness in the sense that the derivatives are the same, and that's optimum. So we kind of obtain we assume something weaker and we obtain something weaker. And as I said, a dominant strategy profile may not exist, such as in this example. These are identical pairs. We can look, however, at this thing we just now did from a different point of view, from the point of view of the mechanism of this proportional allocation. Relative to that mechanism and all those mechanisms we defined with this calligraphic D, you can say that starting from those mechanisms, we actually extended what we allowed. We allowed for personal prices, so we gave it more power. And therefore, we obtained something better. We obtained an efficiency about of 1. We always have an optimum Nash equilibrium. Sometimes we even were able to prove that it's the only optimum, but at least there is one optimum relative to this 3/4. So we obtained something better. In some cases, we were able to obtain it that it's the only optimum. And now, one important thing is that so before there was a unique equilibrium for this game, price anticipation agent. So the unique equilibrium at the price of anarchy or stability, because it's unique, it's the same, which was tightly bound by 3/4. Now we find that at least one equilibrium can be optimal. So that's an improvement. So indeed, we didn't prove that all equilibria are optimum, but at least one is optimum. That's already an improvement because before we had a unique, which is 3/4. Now, under some assumption, we also prove that it's optimum. That every equilibrium is. Indeed, we obtained a better efficiency bound by allowing the prices which uses charts to be different per user. Well, we didn't look at this in this sense. We just said that we charge a certain amount, but we can. I remind you that we can look at this price, and then they were different. So to recap what we have done in the whole chapter, we've looked at the allocation of resources among strategic players. So the resource is fixed. We call it the capital C. There are strategic players who choose how to behave and which utility to function to claim in order to be as well off as possible. We considered several market mechanisms, and the proportional allocation mechanism was optimum for price takers, so those who didn't think of actually the fact that the price was dependent on what they actually did, but assume that the price just was constant, and in that sense they were optimum. That's what's called competitive equilibrium. So for those, the proportional allocation was optimal in the competitive equilibrium, but it was not optimal. There was a bound of a tight bound of 3/4 for price anticipators. So for those who actually realize that the price does depend on what they do, then we also prove that this proportional allocation is also optimum among all the mechanisms which require to be one-dimensional in the input and which may charge a single price. We define this D calligraphic D mechanism. We prove that all of them, and those technical assumptions we need, all of them actually allocated the goods proportional to the bits, but the prices they charge, they could be this or that. That was the degree of freedom, and the way to charge what actually the player, according to what we did in this, what we called in the beginning the proportional allocation mechanism. We showed that it was the optimal montage mechanism, but when that was what achieved this 3/4 ratio in equilibrium. But if we allowed ourselves to extend what we do when the prices depend on the users, then this Scalar Strategy VCG mechanism, which was it's not a VCG, it's something which is inspired from VCG, ensure that there is also always an optimum equilibrium, sometimes even every Nash. Now let's look at several questions for future directions, which immediately flow from this topic. Of course, there are many questions. Let's just look at several. Well, we proved that the price of anarchy bound is 3/4, and that reminds maybe another bound we looked at, but we solved the for non-atomic selfish routing. Remember that work by, I think, Raugard and Tardos. Anyway, that work we looked at non-atomic selfish routing. Selfish routing where there were no players, but actually there were kind of infinitely many players. We just talk about how the flow is distributed, and the bounds were the same, and both proofs also are similar. They both characterize equilibria as optimal to problems similar to the optimization problems, but not the original optimizations, but real optimizations of something else. The question is, can we maybe prove some general bound on the price of anarchy for the cases where the equilibria can be characterized as solutions to optimization problems? Can it be, we prove something general for such? Another question is that we assume for the optimality of proportional allocations, this definition of this calligraphic D, that the utilities are concave. The utilities of price anticipating users are concave. So question is, can we get away without that requirement? Can we prove this, what we proved before, without that requirement? The other question is, what is the exact trade-off between the number of prices and the efficiency? Because we saw that when we allow ourselves to have a price per each agent, and the efficiency can increase. What is the exact trade-off here? Maybe if we allow for 2 prices, then there is small efficiency growth, and if we allow for 4 prices, assume there are more agents, there is a better efficiency growth, and then as the number of prices goes to the number of actual agents, then the efficiency growth goes to optimum or something like that. This kind of trade-off is extremely important in game theory. And the next question is, again, the similar question about the dimension of the strategy space. So if you look at the strategy space, we constrain the strategy space of the VCG, and therefore we had some weaker conclusion because we only spoke about Nash equilibria and not weakly dominant strategy and so on. So what about that trade-off between the dimension of what the player communicates to the mechanism and what the mechanism returns, what they can prove about the mechanism. So those trade-offs are very important, as in general trade-offs in this domain. Okay, so we are done with this topic of resource allocation. And let me know if you have any questions.